So, the title of my talk is, When Are Parallel Oxygenators Necessary? And at this time, we have to know that we can actually have these very large patients that will land on our doorstep in the middle of the night, and we have to think what we'll have to do. So I looked in the literature, and I'm sure all of us that have done adult cardiac surgery we've had that big patient that we can talk about. And I'm sure some in the audience have seen these big patients. I looked in the literature, and actually in parallel oxygenators there's only 4 publications where actually parallel oxygenators were used. On the other side, there are 3 that talk about large patients, and I define large patients anybody above 2.5 meters squared. Now, what I show here of interest is you see in the table how tall they are, how many kilos, surface area, but you don't see a lot of information. What is their oxygen consumption? And that is what we really have to know, because our focus is, can my oxygenator oxygenate this patient? Can I have an acceptable PO2? Is he going to give me trouble because he has a large metabolism? That I have to know. Our onus, what you see in these publications, have mainly been blood flow. And as we've heard today, is blood flow we have to really individualize for every patient. So I'm just going to show you our patients that we had that were over 2.7, and they varied from 2.7 to 2.79 was our largest patient. And living south of Munich and Bavaria, they serve beer in barrels, which means we get a lot of times very large patients, average 130, 120 kilos, no problems. But we see often patients that are 170 kilos. And I have to say, can this little oxygenator oxygenate this patient? So I've taken this data, and we have electronic databases, so I can easily download all this. And when I know I have a large patient, I take extra blood gases, I do arteriovenous, so I can use this data later that hopefully can be published. So you see here, what we have is the oxygen consumption per surface area. Now, I don't downsize patients. I look at the surface area, and I leave their surface area as it is, because this includes the metabolic rate of the patient. And you have here, on bypass, from 81 oxygen consumption per surface area all the way up to 133. So there is a range. We don't know how these patients are going to react. But I can use this information to say the maximum, what we've seen, is 133 mils of oxygen per minute per surface area. And I can use this to my advantage. When you look at the flows, the highest flow that we did run was about 6.6. If you have to look at an oxygenator according to should I use parallel because of flow, you're probably looking at another situation in which you probably would need an extra pump. So, that's right. This is our system. We use the S5 with an external pump here, and by this way we can keep our lines relatively short. We also use the Medtronic Fusion with the integrated arterial filter, and the advantage of this is that our priming volume is about 1,100. It's a very comfortable priming volume. We don't do any wrapping, remove volume, because patients do need volume, but they don't need too much volume. And for these big patients, this is ideal because then we can keep our hemoglobin up to a really good level. So we circulate with 1,500 volume, and then we remove the extra volume that we don't need. And with the innovation that we've seen with the integrated filters, we can keep our priming volumes relatively down. We also have, and this is when we're talking about innovations in cardiotomy reservoirs, is a low resistance cardiotomy reservoir. And in the papers I've read, mostly they've had problems with venous return. Bad venous return means surgeon is in a bad mood, we're complaining about the fact that they didn't cannulate properly, what do we do? But what you see here is with the Fusion cardiotomy reservoir, this curved venous inlet reduces the resistance by over 50%. You also have the size of the tube going down in the reservoir, I lost my mouse, there it is, going from 1/2 inch down to 5/8 inch. So it also reduces the amount of resistance. So it's actually optimizing venous return, and we had no problem with that. Now, oxygenated performance. I did a study on this, and it actually goes up to 420 milliliters of oxygen per minute. When you look at oxygenated performance, we're given this information that's in the book, goes up to 7 liters a minute, and has an oxygen exchange of 420. But we're not given what is the PO2s. One oxygenator can say I go up to 8 liters, but the PO2 is much lower than the other one, goes up to 7 liters. So because this information wasn't available, I had made a study, and it's published in Sage Perfusion 2016 in September. And what I did is I looked at what is the oxygen transfer, of which we see from a patient as being the oxygen consumption, according to FiO2. So I brought it to a clinical level where I would know when I set a particular FiO2 for a patient, what is going to be my PO2 at a certain oxygenator transfer. Because of lack of time, I can't really go into this, but what you see here is on the left side, the oxygen consumption on the y-axis, and on the x-axis, the FiO2. And according to these dots from 2.5 to 2.7, this is how the patients and all the blood gases, these are basically just little pictures in time of every blood gas that I took with the different patient sizes. So you do see here is that even the red, the 2.7 meters squared patients, you do vary a lot with oxygen consumption during bypass here. And actually, you see here, even the 2.5 had oxygen consumption values of about 320. The highest was actually a patient in the 2.6 group that had an oxygen consumption of 350. Now, this 420 oxygen consumption or oxygen transfer is actually extrapolated because we've never ever had a patient that needed so much oxygen transfer. So what we know from this, as I said, is the oxygen consumption per surface area, 133. That is really important information for us to know. Can I adapt this to my oxygenator? So, calculation of blood flow. We've heard a lot about this morning. Lean body weight. I do not use it. I don't downsize a patient. I always think it's like if you go into a store and buy a pair of jeans size 32 and you're actually a 40, you're not doing yourself a favor. So what I do is I use body surface area, which includes the extra body mass. And this is especially important for oxygen consumption, and this has to be measured during cardiopulmonary bypass. And I looked at the cardiac index of 2.4, and I thought, where the heck did they get 2.4? I'd like to find this out. So I started surfing through the net, putting in cardiopulmonary bypass, cardiac index 2.4, and I found this table that is from 1958, and from a Dr. Clark. And what he has here is that he's shown is that if you're a patient with 1 meter squared, you do have a 2.4 cardiac index. What we've lost over the years is he correlated that to a 10 hemoglobin. And that has been lost over the years, but we've kept the 2.4. If you're a patient with 2 surface area, here, the index is actually 2.1. for a hemoglobin of 10. And this actually shows you here, we cannot use blood flow without knowing what the hemoglobin is. So look at this now. If it's one slide that really should be a take-home message, this is one of them. But what I call is calculation of blood flow using hemoglobin. I call it my CQ272/hemoglobin. Now you probably think, what is that all about? Well, what it is I took the minimal delivery of oxygen, which is 272, divided it by the Höfner factor, it gives you an index of 2. If you think your patient is going to have a hemoglobin of 10, that means you just take a 2 cardiac index, not a 2.4, take the 2, multiply it by the surface area, and before bypass, you can say, okay, that'll be whatever size the patient is. Let's say patient's 2 surface area, that would be a flow of 4. And what this does is that it shows you actually with this critical blood flow, the minimum blood flow you should be running. It shows you where are the sharks, where you don't want to go. And anything above that is where you're flowing actually blood flow that's required for the patient on the basis of venous saturation, of pressure, of good venous return. So this actually gives you the minimum blood flow. And you see here, surfer in the water with the shark, is If he goes below this level, he might lose a foot, he might lose a kidney, and that's where we get into renal problems. So you should really know where is my minimum. And with doing this, with the 2 times surface area divided by hemoglobin, when you take your first blood gas, you know where you are. So Mr. Big shows up on the table. He's a 48-year-old male, ascending aortic aneurysm, bypass systems and Medtronic fusion, priming volume 1,100. His height is 179. He weighs 170 kilos. Surface area of 2.74, BMI 53%. Hemoglobin is 14.1. So you start calculating. And what I do is I calculate for my oxygenator performance. Is this patient suited for one system? Which means I start calculating his surface area using 100 per meter squared, using 80 because we're going to cool down to 34 with this patient, and using 130 as an area of reserve is if this patient is really more metabolic active than what I really think, then I know where my limits are. Now you see these FiO2s here, and using this graph that I had showed you where with the FiO2 and the oxygen transfer, you can just draw lines down to what the FiO2 would be to get a PO2 of 150. Blood flow. If you use the CQ272 as 2 times 2.74, my minimum blood flow and bypass would be 5.5 if he has a hemoglobin of 10. And I really think with this patient, I would have at least a hemoglobin of 10. If his hemoglobin is 8 on bypass, it would be a flow of 6.9. So I know where my minimum level is, where I do not want to go or where I don't want to land. I want to be above this. Cardiac index of 2.4 for old time's sake would be 6.6. So this is what I do. I have my graph already made out. We have a sheet of paper at work where we can just draw our lines and everything. So I calculate for this patient what the oxygen consumption would be approximately. So I prepare myself for bypass beforehand. So I know this according to oxygen consumption. And for Joe, a pediatric perfusionist, is that all the oxygenators, you can use this on all size patients. Pediatrics, they have more oxygen consumption than adults do. So this is my 100 line, this is my 80, and this is my 130 with my FiO2s. We're good to go. I'm not at all really, cannot justify in this case to use 2 parallel oxygenators. So what happens? We went on bypass. These are the 4 blood gases that were done, and these are the results. So now I have results from these big patients that I can hopefully share with the perfusion community, which is quite important because we do need more data for these patients. So you see he actually had his highest oxygen consumption per surface area was 107. Blood flow again is his hemoglobin was 11.9. I divide the 11.9 by the 5.5 is 4.6. So this green line, what you see here, is actually where the sharks are swimming. That would be the absolute minimum flow that I would want to flow for this patient. But these are the flows that I did have, 5.3, 5, 5.6, and this is the flow with 2.4. Now, the flow that I did run was based on him as an individual. What did he have for a venous saturation? What did he have for pressure and for the venous return or for the surgeon? Sometimes we have pump flows for the surgeon too. So with this, I can say ideal perfusion. No lactates were built. So this is my last slide. When are parallel oxygenators necessary? My largest patient was 2.8. I would have no problems going up to 2.9. From 2.9 to about 3.2 is a gray area. We don't know what's going to happen with these patients, whether they're going to be so metabolic active that one oxygenator would not work. So put in 2 connectors and have an extra oxygenator ready to put into circuit. So what I do here is, depending on their oxygen consumption per surface area, 2.9 times 30 would be 377, wouldn't be a problem. If they're young, if they've got a lot of muscle, if they have high triglycerides, then you might want to calculate up to 150, which is 435. Then I would go into using a parallel oxygenator for this patient. Blood flow, maximum blood flow should not be a limiting factor, but you can calculate your blood flows based on hemoglobin. And you need a nice small system to reduce the hemodilution. Now, after 3.2, I would definitely put in an extra oxygenator as a reserve, but till now I haven't seen such a large patient, but you never know, maybe somebody out there will. So enjoy your lunch and catching up with your colleagues, and I wish you all a good Venus return. Thank you.
So the German beer must be good then.
It is, I love it.
Any questions for Carol on this presentation?
Have you validated the oxygen transfer curves in other oxygenators besides this particular one?
Yeah, yes I have. Yeah, and it works quite well.
Does it stay constant during the procedure? Do you find that as oxygenator, in other words, sometimes oxygenators deteriorate over time because of fibrin formation and...
It pretty well stays constant until about 9 hours.
Okay.
Yeah, so.
Okay, good. Any other questions? All right, well, thank you very much indeed. There's a little something. Okay. Good. Well, that concludes the session. Just to remind everyone to come back at 1:30. One of the entries in your program says 2 o'clock, but the speed dating with industry starts at 1:30, and lunch is served outside. So thank you very much, and to thank all the speakers.